how's it going, y'all? We're the Clutchstones, and we've been working on this push button shifter since project management. I'm Colin Daff, the inventory specialist. This is Sammy Suarez, head of R&D. Ivan Tonich, electrical lead. Sarah Gallman, project manager. Duran Garner is our manufacturing lead. And Sylvia DeTore, our scheduling coordinator. And our mentor is Mr. Carlson. Special thanks to him for working with us, being our mentor. Our goal is to make a custom design part, especially for our customers' needs, and in this case is Mr. Carlson. And we're going to use the knowledge that we've learned over the past 4 years in the school to get that done. And it's to design and produce an electrical shifting mechanism for a 1969 Volkswagen Beetle transaxle with an H-pattern manual transmission. And we're going to control this with a row of 6 push buttons in a row, and we're going to connect 3 DC stepper motors to the Arduino board to power the shifting of the gears, and this will be through rotational and linear motion. We'll get more into that later. It's the same.
So a little background about push button shifters dates back to the 50s when Chrysler released a push button shifter for a 2-speed transmission, which had reverse, neutral, drive, shifting 1 and 2. The only difference between that and our project is it was automatic, and ours is a electric powered manual transmission. The difference with the project that we're doing now in modern day vehicles is that we are using a transit axle from a 69 Volkswagen Beetle that's going to be mounted on an O2 Ford Ranger. Okay. So these are kind of like the classes that we use throughout our project. We use manufacturing process for the lathe machine to turn and bore. Material science for our material selection. So instead of using aluminum, we use the steel shaft because the transmission shaft is also steel. We use digital systems for logic signals, circuit analysis to connect wires and programming, and project management to determine scope, schedule, and cost.
Okay, so now I'm going to talk to you all a little bit about the mechanical plan. So first, we're going to be manufacturing a shaft to extend off the transmission shaft. This is going to help with the linear and rotational motion. Then we're going to make a coupling that's going to attach into the shaft. That's also going to help with the linear and rotational motion. Then we're going to make a modular box, which is going to hold all of our Conduinos and our electrical components. And this is going to be modular, so you can move it wherever you want. And then, of course, the assembly of the coupling to the shaft and of the modular box. So our material selection for the shaft and coupling and the L bracket. So we decided to go with carbon steel because originally we were going to go with aluminum, but since aluminum is a non-ferrous metal and steel is a ferrous metal, that would cause corrosion over time. So that's why I decided to go with carbon steel. And we got this shaft from scrap in the shop because there was no cost to the team. Now how we machine the shaft itself. First, we used a turning operation that Sammy had talked about earlier. This turning operation, we used it to first get the coating of rust off the shaft. We then that took a number of passes. Then after we got that coating off, we then used the turning operation to get the diameter of the shaft itself down to 1.03 inches. After we got the shaft diameter down to where we needed it to be, we used the tailstock assembly on the lathe machine to drill a hole of 0.79 inches into the shaft itself. Then we used the boring cutting tool on the lathe machine to get the diameter down to 0.55 inches. We did this so this could fit onto the actual transmission shaft, which had a diameter of 0.55 inches. Then lastly, we used sandpaper. We turned the RPMs of the lathe machine down to a lower RPM. We used different grades of sandpaper, as you can see in these 2 pictures right here, to smoothen out the shaft and give it a nice clean finish. This is the final product right here. Next was the machining of the coupling that goes to the end of the assembly of the end of the shaft. handheld sander to get the coating of rust off it because it is a carbon steel. After we did that, which took quite a while, after we did that, we then spray painted the coupling blue and used the height gauge to measure out the dimensions of the shaft so we can assemble it to the end. We cut out that assembly. And then Ivan's going to talk to you a little bit about our electrical equipment.
Okay, oversee we can see electronic schematic of the electrical system. On the top we have 3 stepper motors, in the middle stepper motor drivers, and Arduino Uno who's going to carry a software, and on the bottom we have a pin in. It's a pin in out, pin input. And this pin input is required to connect a command board, push button board. Motor 1 is going to operate clutch lever. We need only one motor for the clutch because clutch lever goes forward and backwards. Motor 2 and 3 will operate the shifter. We need 2 motors, one motor to operate forward and backwards motion, the other motor left and right motion of the shifter. Each motor has an independently driver, and we require drivers because we are not able to connect directly Arduino to the motors because motors require high voltage. So driver has a purpose to accept the 0 to 5 volt signal from the Arduino, and the driver will control with that signal higher voltage to go to the motors. Arduino only have 0 to 5 volts, which is a digital signal. Next slide, please. Over there, we have a prototype circuit. We use the prototype circuit to do experiments, to do coding, and to do functional check because it's much cheaper than real elements which we're going to use on our project. So far, our hardware is completely solved and it's completely operational and functional, and I'm going to show you how it works. Here we go. So far, we are using only a sampling code which is provided by the Arduino site, and unfortunately so far I can control with that code only 2 motors. It can be motor 1 and 3, 2 or 3, or 1 and 2, doesn't matter. And right now we have only simultaneously motion of the motors, and but we require the sequential movement of the motors. And next slide, please. Oversee we have a code, and for our future tasks we have to develop proper software for this system.
So for our test and experiment plan, first we start off, we had to make an inventor drawing. Here's a drawing. This is our shaft and couple that we had machined in the shop. The green part is our shifting shaft. That's basically a gear selector, goes between first, second, third, and fourth. And then so to make this work to test, we're going to have to get a 3-phase DC motor and connect it to a variable frequency drive on the input shaft of the transmission, so we can get a full load of the transmission. We get a test of the full load while it's under full load. So the text fixture simulates a vehicle's internal combustion engine and operates the input and operator's input. The Arduino controls the VFD by issuing output signals to the VFD, which vary the speed of the 3-phase motor. This allows the electric motor to drive the transmission input shaft at varying speeds. The Arduino controls the VFD. The Arduino controlling the VFD generates an output signaling load to be processed by the Arduino controlling the transmission. So here's some tasks that we still need to complete. Is the manufacturing component assembly, then mount the component assembly to the text fixture, configure the motor with the Arduino and VFD, connect the Arduino VFD and motor assembly, test operate operation of the test fixture itself, and then mount the transmission to the test fixture. Next slide. So here's our stress analysis of our assembly. So we have our coupling right here. This is our displacement. So on the coupling, it displaced under 30 pounds per inch of load, which is well beyond what we're doing. Our load will be probably between 12 and 15 pounds. And it shows our deflection on top, so we could make that a little bit thicker on the coupling, so it doesn't deflect as much. And then our von Mises diagram shows our failure between our push-pull motion of the shaft, and then we have our first principal stress analysis.
So you can see here is our spring 2019 Gantt chart schedule. So each task is assigned to a certain member. And as you can see, our fall 2019 schedule for all our tasks that need to be complete, and again assigned to each member. We're in the implementation phase right now with the gears and making sure that the code is correct for the three motors, make sure those all work together. And then once we have that, then we can test everything as one assembly. So this is our budget. We've only spent around $300, so we're way under budget. To conclude, our assembly, like Sylvia said, is modular. So anything that any group wants to do in the future, they can move around. They can move the electrical, they can move the motors. We're hoping to complete our project by November 22nd. That includes the coding and all testing and assembly. So to complete this, we need to design and build the command board, test the Arduino coding, and test our final system as one assembly. To complete everything, we'll do one more final presentation in our final report.